To set the context for this video, we're going to watch an airliner take off from Melbourne Airport in Australia with a strong crosswind. I especially want you to note what happens to the aircraft when the wheels leave the runway. While it is on the runway, you will see it tracking nicely down the centre line. After takeoff, something else occurs. So as you just saw, as soon as the aircraft left the ground, it was pushed sideways by the crosswind. It adopted the velocity of the wind in addition to its own airspeed, and that is why it was drifting away from the centre line of the runway. Now this is important when we come to understanding why the Coriolis effect is not such a big issue for aircraft at all. In addition, the pilot can take corrective action and offset that drift to remain in line with the centre line of the runway, as you will see in the following footage. So this video was taken a few years ago when I took my wife for a flight in a light aircraft for one of our anniversaries, and you will see shortly after takeoff I angle the nose of the aircraft to the left slightly to compensate for the crosswind, and by doing so the aircraft is then able to track more directly in line with the centre line of the runway on the upwind leg. Note especially the position of the vertical fin during the takeoff roll and immediately after takeoff. And this should also silence those flat earthers who complain about never seeing my face and never seeing any proof that I'm a real pilot.
Okay, we are good. Thanks, down tower. Good afternoon. Zulu X-ray India is ready, 29 right.
The Robin ready at right, say again.
Zulu X-ray India ready, 29 right for a right crosswind departure.
Zulu X-ray India, runway right, clear for takeoff.
Runway right, clear for takeoff. Zulu X-ray India. Okay, there we go. Lima, requesting backtrack from the main pad, just 100 meters to the final approach again.
Lima approved.
Approved to Lima.
Look at the position of the vertical fin now, and then when the aircraft becomes airborne. You can clearly see the adjustment to the heading of the aircraft to compensate for the crosswind. So the key points I'd like you to remember from those two clips are that 1, with no heading adjustment, the aircraft will drift sideways with the wind, and 2, by offsetting the heading intentionally, the aircraft can be made to follow a desired ground track. Now that is highly relevant to navigating precisely around the Earth, because that is exactly what we do in the aircraft. We offset the heading as required to compensate for the Coriolis effect and the effect of any wind to achieve a desired ground track. So in recent weeks we've had some extremely strong jet streams across Australia, and this is footage taken from a flight that was tracking south across the jet stream. And here you can see the indication of the wind, 165 knots, and it's basically all crosswind. Just to explain the footage, this magenta needle is indicating the ground track of the aircraft, and this small white arrow represents the heading. So as you can see, there is quite a split, and that is how much heading offset is required by the aircraft to achieve the desired ground track. Now later in the footage, I pan down to the flight management system where you can see more accurate data. There we can see a cross-track error of just 0.01 nautical miles, and that is about 60 feet which is less than the wingspan of the aircraft. We can cross oceans and fly 6,000 nautical miles without ever being more than one wingspan off course. As you can see here, even with 166 knots of wind, broken down to 88 knots of headwind component and 140 knots of right crosswind component, our cross-track error is negligible. Our ground track is 203 degrees. The heading is 221 degrees. That is the direction the aircraft is pointing. This is the path it is moving across the ground, a drift angle of 19 degrees. So the aircraft is more than capable of offsetting its heading as required to maintain a very precise ground track, even with strong crosswinds like this. So we're now going to look at the Coriolis effect, and you will understand why this effect is quite insignificant when it comes to navigating an aircraft. Just to refresh our memories on what the Coriolis effect is, it is due to the rotation of the Earth and the fact that the Earth is rotating at a steady angular velocity, and that means the equator, being the largest radius, is going to be moving at the fastest speed. As we move away from the equator towards the poles, the speed of the movement of the ground will become slower. So if we had a firearm at the equator and we fire a projectile, it initially has this velocity at the equator, but that velocity will cause it to deflect away from the line of longitude and move ahead like that. If we were at a different latitude and firing towards the equator, it would actually lag behind. And it is this effect that produces opposite rotation in the weather patterns and is also the reason why no hurricane can ever cross the equator. One of the mechanisms for a tropical cyclone is the Coriolis effect, and that reverses as you cross the equator, and that is why we will never see a tropical cyclone crossing the equator. So let's take a look at a scenario where Coriolis may affect our aircraft. And remember, the aircraft had no trouble at all compensating for 140 knots of crosswind. Looking at a flight from Bali, Indonesia to Perth, Australia, it is almost directly south, a direction of 178 degrees, and the flight time is approximately 3 hours. So what we're going to look at is the difference in the speed of the Earth's rotation at Bali and Perth, and see how much that changes over the 3-hour flight. Bali has a latitude of 8.34 degrees south. The speed of the Earth's rotation at Bali will therefore be 1,040 miles per hour times the cosine of 8.34, and that is 1,029 miles per hour. In Perth, the latitude is 32 degrees south. The speed of the rotation is therefore 1,040 miles per hour times the cosine of 32, giving us 882 miles per hour, a difference of 147 miles per hour. The flight time is roughly 3 hours, so we have 180 minutes. We have to change our lateral velocity by 147 miles per hour in 180 minutes, and that is roughly just less than 1 mile per hour per minute. Now, it's not exactly linear, but for the purpose of this explanation, you can see that the values are very low, just 1 mile per hour per minute, and that equates to a crosswind of less than 1 mile per hour. The aeroplane has absolutely no trouble compensating with 140 knots of crosswind, so you can therefore understand why this effect of Coriolis is insignificant. So the aircraft does whatever it needs to do to maintain the desired ground track. But let's consider something else. Let's assume there was no wind and the atmosphere was matching the rotation of the Earth perfectly, and we simply maintained a constant heading and did not make any adjustments for the ground track. Remember what happened to the aircraft shortly after takeoff in a crosswind. It immediately adopted the motion of the wind. And that is exactly what would occur if an aircraft was flying from Bali to Perth with the atmosphere matching the rotation of the Earth perfectly and the aircraft making no adjustment. As it continued moving south, it would be moving into air that has a lower lateral velocity, and that would cause the aircraft to begin moving with the air. So the Coriolis effect is even less of a problem than we first imagined. And a question I have seen a few times from flat earthers is, why do we have to calculate for Coriolis before firing a gun, but we don't have to make a calculation before taking off in an aircraft? And the answer to that is very simple. The aircraft is making constant corrections en route. It is adjusting the heading as required to achieve the desired ground track. A bullet cannot adjust its flight path mid-flight, so any correction for Coriolis has to be applied before firing.